Here's a quick example, which I also put into a problem that I did on the board, but the problem on the board is longer and has this as one piece. So I'll mention this one anyways. The limit as n goes to infinity of e to the 1 over n. You can replace the n with x and try to take that limit. And then when you plug in infinity for x, 1 divided by infinity is 0. In other words, the limit as x goes to infinity of 1 over x is 0. And so then e to the 0, which is equal to 1. Next for 11.2, time to move on to something called series. So, in English, sequence and series usually are synonyms. A sequence is a bunch of stuff in a row, and a series is a bunch of stuff in a row. But in math, nope, it's different. In math, whenever somebody uses the word series, they ought to be referring to the sum of a sequence. So, when we were writing down sequences, basically we would put commas between each term. It would just be the outputs. But a series, you put a plus between each term. So for an example, here's an infinite series. N equals 1 to infinity, summation 1 over n. Now that big sigma, you have seen some places before in Riemann sums, it means add every time, and it means start at n equals 1 and then go up by 1 each time, so that the result of this is 1 plus 1/2 plus 1/3 plus 1/4, and it goes forever because the top is infinity on the big sigma. So recently we did some integrals that ended up at infinity but still often had a finite value. That's what's going to happen here too. You can have these add up to either infinity or to a real number. Whenever something ends up in infinity, we say it's divergent. Whenever it ends up at a real number, we say that it's convergent. You say that for the integrals, for the limits, and also for these infinite sums. So here's an example. We better see one that does end up at a real number. So that's n equals 1 to infinity, 1 over 2 to the n. So plugging in n equals 1, you get 1 over 2. Plugging in n equals 2, you get 1/4. Plugging in n equals 3, 1/8, then 1/16. All the powers of 2 as denominators, and they add up forever. So this infinite sum actually does get closer and closer to a real number. And the best way to see that is with a picture. So here's a picture. So this is a square of both sides size 1. It's a 1 by 1 square. And my series, the addition up there, says start out with 1/2. So on the left, I put a half of the square. I wrote 1/2 in the middle, shaded it in a little bit. So you can see the punchline since I had to draw this ahead of time. The next term is 1/4, and I add that on by cutting the other half in half and coloring it in. So a half and a fourth. So far I've got 3/4 of the square. But then the next term is an eighth, so I can cut that last fourth in half and add it on. And the next term is a 16th, so I can cut that last eighth in half and add it on. And then so on. Every time to add on the next term of this series of fractions, I cut what's left in half and then shade it in. And you can tell that that's going to get closer and closer to filling the box. Every time I add on a new term, I'll add on half of what's left. I'll never get larger than the box, but eventually I'll fill it in. Eventually as in the limit as you go to infinity. So that's what I say. The limit as n goes to infinity of I equals 1 to n, where you stop at n instead of infinity, of 1 over 2 to the I. So that'll be what's called partial sums of the series. I don't go all the way. But then if I take the limit as n goes to infinity on that, I will get 1. There's a few of the terms that you can see. At 1 I get a half, at 2 3/4, at 3 7/8. So basically, if all the terms in a series are smaller and smaller sections of a geometrical shape, and each of them fit into whatever's left, then you can get that the limit goes to a constant real number. We have seen the idea of an infinite series that goes to a constant real number before. Here's a quick example. If I take this series of fractions, I won't try to write it down as a formula, but just see the series of fractions. 2 plus 7 tenths plus 1 100th plus 8 1,000th plus 2 10,000ths plus 8 100,000ths plus 2 millionths. And the pattern for that is that this is just the decimal expansion of 2.718282, which is E. So anytime you have an infinite decimal expansion, that is a series which is approaching a real number. Any decimal expansion, because you can put any decimal expansion you want, and it'll always get closer and closer to being an actual real number. If it's an infinite repeating decimal or an infinite not repeating decimal like E, still gets closer and closer to a real number.